And we're started. So now we're going to do section 6.3, day 1. There are 3 parts to section 6.3. I break it into 3 parts because it's all volume. 6.3 is volume of solids. Day 1, is going to be volume by known cross-section. Everybody okay with that? Doesn't matter. Before we can start, we need to have a cross-sectional area. So we have to talk about each one of those cross-sectional areas. So cross-sectional areas, cross-section, X-section means cross-section, it's abbreviation, or an approximate. X-section areas. If you don't know the formula for the areas, this gets very difficult. So we're going to go over it. So suppose I have a cross-section that's a square. The way this is going to work is, it's square. You're going to have some length that goes between your curves. Remember the length of the rectangles? It's that same length, the upper minus lower, right minus left. So if you can't do area, you can't do cross-section. Just saying. The way this works is, since it's square, whatever that distance is, the upper minus lower, right minus left, it's going to have that same length coming out of your paper. And then there's going to be a width to it, and that width is delta x, or delta y. Since it's upper minus lower, it's delta x. That's going to make a volume, and first we start with the area. So this area right here is equal to length squared, right? So what we do is we integrate the length squared between A and B dx, and dx is this width here, and I get 3 dimensions. So volume is going to be the integral of area, dx or dy, so that means volume is equal to the integral of L squared dx from A to B, and that's true of all squares. You just have to find out what the length is, that same upper minus lower that you did for the area. And I teach you the way I teach you on the area so that you're doing the same operations over and over again, so you don't have to learn some different technique. Just adding on. So squares are the easiest. That's the base shape. You start with that. Then there are semicircles. Semi means half. For semicircles, the shape, it's a semicircle. It has a width that is, in this case, it's delta x. All right, so this is a diameter. Your diameter equals the length for a semicircle, not the radius. So if you want the radius, is it L over 2? You just have to keep that in mind. So what's the area of this cross-sectional area right here? So the area is equal to 1/2 of a circle, which is pi r squared. So you either have a choice of, I'm just going to do it, d over 2, all that squared, right? Oh, I didn't do that right. Hang on. All that squared. So if we simplify that, and we do it in terms of L, then this becomes, because L is D, well, we have 2 squared, which is 4, times 2 is 8. So is this pi over 8 L squared? Does everyone see where I got that from? I want you to know where I got it from. You can just memorize it, or you can understand where it comes from, so that if you have a bad moment on the test, you just have to go back and figure it out again. It's half of a circle. in diameter, you take half of that to get the radius. You got to square it. That's why you get a fourth, but since it's a half, it's an eighth. Everybody got it? Okay, and then this is where it gets fun. Equilateral triangles. You should have learned a formula for this. You should have used it last year, and you probably didn't. Whatever. Equilateral triangles. It's okay. So what does that look like? Equilateral triangle. It has a width. This is delta x. This is L. This is L, but that's not how we find the area of a triangle. We find the area of a triangle with the height. Since this is equilateral, each one of those is a right triangle, right? And so that means this length is square root of 3L, half of L, because it's half of L. It's just easier if you will just memorize this formula. Area is equal to square root of 3 over 4 L squared. That is my 2, 3, 4 formula. You're squaring the length, multiplying by the square root of 3, and dividing by 4. 2, 3, 4. 2, 3, 4. It's based on, if you look at this, half of it, it's a right triangle. If this is L over 2, then this is double it, so that's L, and this is square root of 3 over 2L. If you remember any trig, it's easy to figure out, because you're just going to do L times square root of 3 over 2L, and that's how we got that. That's how I got that, because it's 1/2, right? Everybody understand? And you're doubling it. Anyway, remember it's square root of 3 over 4 L squared. So it's a 2. There's a 2 is the square, the 3 is the square root, and the 4 is the denominator. Those first three, the square, the semicircle, and the equilateral triangle, are the most common ones used on the AP test. That doesn't mean they're the only ones. Occasionally they do a isosceles right triangle. I think last year they did it, and I went, oh boy. So anyway, then there's isosceles right triangles. You have a choice. The one I showed you on the video, the sketch, it was the one where the length is the leg, right? If that's the downside, it's really easy, because that means this is L square root of 2. Who cares, because what's the area? Area is equal to length squared over 2, right? Because this is a leg and that's a leg. That's the easy one. The hard one is when they put the hypotenuse down. Because this is x, and this is x, and this is x squared root of 2, which that equals L. So we have to solve for x, because we generally have it, so even though we have L, to put it in the formula, do I need these two? So x is equal to L over square root of 2. That means this is equal to L over square root of 2. And this is L over square root of 2. So when I go to find the area, it is going to be L over square root of 2 squared, and it's times a half, right? So 1/2. When I square that, I get area equals to L over, well, it's 2 times square root of 2 squared, which means it's just 4. It's not, that's squared. It's not a hard formula, but remembering it's a really simple formula, but remembering why it's that way. Why do they like this one over that one? Because this is really, that one's pretty straightforward and easy, but this one is tricky to get to, but it's really easy if you know the formula, or you can get to the formula. Integrating is really easy. That's why they like it. Because the calculus part is easy. It's the geometry that's hard, because you don't remember that stuff. Okay, that's the background. That's the cross sections. What does a problem look like? It looks like this. Actually, I'm going to change pages because I need a fresh page. So this is example 1. Find the volume for a base area between y equals square root of x, y equals 0, x equal 1, and x equals 0, with cross sections of squares perpendicular, and that's going to matter, to the x-axis. Okay, when it's perpendicular to the x-axis, when you were doing Riemann sums, that meant it was with respect to x. When you were doing areas, if your cross-sections are perpendicular to the x-axis, it means it's with respect to x. So in all of these problems, whatever it's perpendicular to, that right there tells me with respect to x. So do you have to read carefully? Because can we also do these with respect to y? And then do you have to solve for x and get everything in terms of y, including your limits of integration, and do this volume problem just like you did those other area problems like from yesterday? All right. So we need a sketch. Oh wait, did I give you? Yeah, I did. So we need a sketch. That's really easy to sketch, right? It's a sketch. We don't need a beautiful drawing. We don't need a Monet. We don't need a Picasso. We need a Mrs. White special. And I'm just going to make it up what my 1 and my 1 are, right? And I'm going to, what did I say? That's not supposed to be a 0, it's supposed to be a 10. Oops. That's 10 right there. That makes a big difference. Okay. So we are going to just kind of swag it. Do you know what swag means, right? No, scientific wild ass guess. Swag. We're going to swag it in. So we're swagging this in. I'm just going to say that, let's see, 2. Well, we'll say that's 1, and that's 1. And then we're going to, it's not to scale. I'm just going to say this is 10 down here. I'm not going to worry about it. I just want something reasonable to aim for. And I'm going to put in my square root. Don't worry about it being to scale, because remember, it doesn't matter. We can label things whatever we want to. So that's one of the things I have to bound it, right? What else did they say? They said y equals 0. Well, that's this line right here. That's another one. So I got y equals 0. I got, this is y equals square root of x. And then my limits, they're my limits of integration, but I have 2 more lines. And those are x equal 1, this right here, and x equal 10. If we were doing an area, we would be doing, let me see if I can find another color that I need. Oh yeah, that bright pink, that'll work. We're doing cross sections like so. This would be like if we were finding the area under the curve, right? But that's not what we're doing. Each one of those, instead of just being a rectangle, is now a prism. So if I take one of those and draw it down here, oops, not move this, move this. If I take one of those, I'll take one of those cross sections, one of those. And we put, that's L. Well, coming out of the paper, it's coming out of the paper, right? And that's one of those, and there's going to be, and each one of those has a teensy beensy weensy width, right? Because it's a prism. That is delta x. That n is delta x. Do I have to find the length? Because this area is equal to length squared. So we take one of these and we go, oh, the length is equal to the upper minus the lower, which is the square root of x. Does the x equal 1 and x equal 10 give you your limits of integration? Do y'all see it? I'm integrating from here to here to fill this region with those prisms. And guess what? It's a limit process, right? So its limit as the number of prisms approaches infinity, right, of the summation of I equals 1 to n, and I have some area, each area of each one, right, and then delta x, and I'm going to make my delta x the same width every time, right? Is that the area of each little prism? And I'm going to add up the volume of each single one of those. Is that going to give me my total volume? Is that whole thing equal to the integral from 1 to 10 of the area of each one of them, dx? And in this case, since it's squares, is that going to be the integral from 1 to 10 of L squared dx? And my L is the square root, so it's the integral from 1 to 10 of the square root of x squared dx. OMG, does that get any easier? Volume is equal to the integral from 1 to 10 of x dx. What's the antiderivative of x?
X squared.
Over
2.
Evaluated from 1 to 10, so my volume is going to be 100 over 2 minus 1 over 2, which is 99 halves, which is 49.5.
Tutto è più facile.
Yeah? That was pretty facile. Yes? Easy? I mean, the calculus was easy, don't you think? Getting to the calculus, not so easy. In this case, the geometry's killer. But instead of, the limit process when we were doing area and we're doing integration, it was just adding up rectangles. Now we're adding up prisms. So you need to find area, and that's where the geometry comes in. And it gets a little complicated. But that was pretty easy, right? Can we do semicircles? Can we change it and do that same problem and just do semicircles? What's the only thing that's going to change if I change the cross sections to semicircles? The coefficient. For the area of a square, it was L squared. For the area of a semicircle, it is pi over 8 L squared. So if you just found the volume using squares, do you need to take that same volume and multiply by pi over 8? I'm serious. The volume of a semicircle, of semicircles, is equal to pi over 8 times 99 halves. Really, really. And if I want equilateral triangles, do I take the same L squared and just multiply by square root of 3 over 2? If I want equilateral triangles, it is equal to square root of 3 over 4. I probably said it wrong. Did I say it wrong? Yeah, I was saying over 2 and I was doing trig. It's equal to square root of 3 over 4 times 99 halves. So the basic technique is the square, because that's the length squared that you're integrating, and then the question is what's the coefficient? If it's a square, the coefficient is 1. If it's a semicircle, the coefficient is pi over 8. If it's an equilateral triangle, the coefficient is square root of 3 over 4. Those are the three most common. Really, really. Do we stop at that? Oh, no. Now we got to do, I need a whole new page. Now we're going to do, what if I'm doing cross sections perpendicular to the y-axis? This is example 2. And then y'all get to work. Find the volume for a base area between, did I mention that my favorite curve is square root of x? Yeah, we're going to still do it. Square root of x, y equals 0, and x equal to 9 with cross sections perpendicular, that symbol means perpendicular, to the y-axis. Of equilateral triangles. What does perpendicular to the y-axis mean? With respect to y. Okay, before we get carried away, can we sketch this without doing the whole respect to? We can. So we're sketching. It's between square root of x, 0, and 9. And actually, that's pretty darn easy. So we do our... It's a sketch because it's square root of x. We don't have to be real... We don't have to... It doesn't have to be great. Wonderful. So we're just going to wing it in there. This is going to be a serious swag. There we go. That's y equal to square root of x. And then I want y equals 0. Here's y equals 0. And my last one is going to be x equal to 9. If x equals to 9, what is y equal to? 3, right? Square root of 9 is 3. Agreed? I don't care if it's to scale. Remember, this is just a sweat. We just need a sketch. Everybody okay with the sketch? What are our cross sections perpendicular to? The y-axis. So are they like this? So if I'm doing my length, I'm doing one of these lengths. What is this length equal to? And this time I don't want upper minus lower. I want right minus left. What is the equation for the right boundary? It's x equal 9, right? So it's just 9. Because it's going to be the x, because we're doing everything in terms of y. So it's 9. My y is 9. Not my y. My x is 9 every single time, right? And then, my height is 9 every single time. It was height. So the y is 9 every single time. And it's minus, have I got a problem here? Do I need to solve for x? Yeah. So right here, we're going to square both sides, and we're going to get x is equal to y squared. So what is my right boundary? Is my right boundary every single time going to be the x equal y squared? So L is going to be 9 minus y squared. Do y'all see where I got the y squared from? This is x equal to y squared. This is x equal to 9. My length is 9 minus y squared. What are my limits of integration? What is a going to be? What's a? What are my limits of integration going to be? It's going to be 0. And is this b? 3. So I'm integrating from 0 to 3. So I'm stacking cross sections like this. And what do my cross sections look like? They're equilateral triangles, right? So I'm stacking a bunch of equilateral triangles. So how would I write the integral? My volume is going to equal the integral. What's the coefficient for equilateral triangles? Square root of 3 over 4. I'm integrating from what to what? 0 to 3. Are those y values? Yes. Because remember, it's all with respect to y. What is my length? 9 minus y squared. Are those y values? Y, is that y? It's a y value for the 9, and it's a, because it's constant. And it's a y to describe this function, yeah? And it's respect to dy. So it's respect to y, it's dy. Square that, so you're going to get square root of 3 over 4. And it's integral from 0 to 3, and what's 9 squared? And then when I can y'all do that in your head? Because it's going to be 9 times negative y plus 9 times negative y is negative 18y squared. And then negative y squared is going to be positive y to the 4th dy. Is that going to be a piece of cake easy to integrate? It's a polynomial. Wait, what? How did I do what? Algebra? How did I do algebra?
No, you didn't square the L.
Oh, sorry. I didn't write the 2. I was doing it, but I didn't write it. Thank you for catching that. Yeah, I'm squaring it because it's L squared. I just went on and did it. But to be honest, I don't normally write that down. Y'all should. But normally I just look at that and square it and go on. All right, let's finish this one. Square root of 3 over 4. What is the antiderivative of 81? 81y, ask y. And then it's 18. What's the antiderivative of y squared? You can go ahead and get it to 6. I mean, you don't have to write this. If you know that it's 6, go ahead and do it. Just be careful. What is the antiderivative of y to the 4th? And I'm evaluating from 0 to 3. You could simplify that. That becomes 6. And then our volume is equal to square root of 3 over 4 times 81 times 3. Just write it down. Oops. I can't talk and write at the same time today. Not surprising. 81 times 3 minus, okay, I got 6 times 3 cubed over 3. I want to make my life easier in just a second.
The 6 was reduced.
Huh?
It's a 6 one. You don't have to divide by 3.
Oh, you've already done it. You're right. We've already done it. Space Cadet. Okay. Then this is 3 to the 5th over 5. Minus 0. And don't worry about it. That's close enough. You can do the math later. Right? You could factor out a 3 over it. It doesn't matter. Whatever you want to do. But that wasn't that bad, was it? So now you get to practice. I'm done.